So, yeah, hello, welcome to pattern analysis. We continue with our conversation about, let's say, very basic models of random variables, but we will leave this then next week and go to more, let's say, to a more bird's eye view on individual things. But okay, like for today, what we looked at was this relationship. What if we have a conditional probability that one variable is conditioned on another? And in particular, we looked at Bayesian networks, and then there was also the conditional independence as a somewhat complicated, slightly more complicated aspect of the relationship of different variables. And I want to, like, the purpose of today's meeting is to follow up on that. I also, in the video, I was also mentioning, yeah, you know, there's this example with this burglar and the earthquake and so on. So I brought a book that spells this out, like step by step, also numerically. And what I would like to do today is to go through these equations like one by one, just to drive this point home and to understand, like, okay, if we have evidence for one thing, then it changes our belief about the other thing, and just go through that calculation. I also scanned these pages and put them up in StudOn such that you can follow up on this on your own. But we also we are going to talk about this also. Before we look into this, one organizational thing, someone made a remark about the material for last Thursday's class. We will also upload this. This was promised, and of course we will keep this promise. It was just that I had a follow-up question on, okay, like, is this solution the way how we really want to have it, and so on and so on. So we have a conversation about that tomorrow, and then we're going to upload the final solution in a way tomorrow or Wednesday or so, before Thursday. Yeah? Okay. Upcoming Thursday, we will follow up a bit with some illustrations, some more illustrations on these conditional independence properties. So yeah, I hope it will be helpful. As usual, I prepared a little worksheet for today. We can read through it in a minute, but before we start with that, I wanted to ask you, is there something in particular that you want me to address, maybe something to follow up on the slides, the video or so? Then we could do it now. Of course, you can also later, like anytime later, come up with something. Okay, I mean, we can just start and have a look here at the things I wanted to discuss today. So the first thing is this Bayesian linear regression. I just wanted to follow up on that. Yeah, sorry. Mm-hmm. Yeah. Yeah, I mean, okay, so so there's a certain disconnect, I would say, between the visualization of things, which in 2 dimensions is very convenient, very easy, and the math, which easily scales up to 100 dimensions, or like in this text image model CLIP, it's 768 dimensions. Why not? No? Visualization, I mean, on paper or on a blackboard beyond 2 dimensions gets messy. No? Of course you can draw it. No? You can do a 3D projection onto 2 dimensions. You can also project 4 dimensions onto. At the cover, sorry, this is unrelated, but on the cover of my, like the equivalent of a master thesis, I wrote a so-called Diplomarbeit, but anyways, it was like a master thesis. I projected a 6-dimensional hypercube. So you can do it, but it's not getting necessarily clearer. And in particular, what you will observe is this, we are going to talk more about this later. There's a certain disconnect in the intuitions, like what you would expect about distances, because the way how, like what we're seeing and what our experience is a 2 or 3-dimensional space. And it turns out, if you say, oh, we have a uniform distribution in a 100-dimensional space, turns out that this behaves differently than what we would expect. And this is very confusing in a way. And it also doesn't necessarily get clearer when you say, okay, now I draw a projection of a 100-dimensional space onto 2 dimensions or so. No? Yeah. Sorry, the last sentence?
Some concepts are difficult to understand in higher dimensions.
Yes, some concepts are different in higher dimensions. Some problems behave differently in higher dimensions. This is all true. But there's no way to do a faithful visualization of that. We will discuss this a bit more when we talk about manifold learning. Or is it dimensionality reduction here? So early June, we're going to talk more about this. Yeah. Yeah. But at the end of the day, it's like high dimensional spaces is just math. No? So there's no way around the math. So these visualizations are an attempt to make it look more friendly, no? But it only leads so and so far. Okay. Shall we have a look at this Bayesian linear regression? So I assume that more or less all of you are familiar with normal linear regression, because this is what was covered in pattern recognition. It was probably also covered in some other machine learning class that you attended. But the Bayesian and Bayesian linear regression, this is a particularity. Yeah? Okay, you want? Yeah.
One more thing is that in like your first lecture recording, you didn't take the pattern.
Okay, but it's a recommended prerequisite for the class. So you have to take a bit care of this also on your own. Huh? So because I do have to make assumptions about what people studied before and what they didn't. So I'm aware of this, but this is at anybody's own discretion, because I have to build on something. This is a master's class, first of all, and it's not the first master's class. It's supposed to be the end of a chain of events. So yeah. Mm-hmm. But we discussed this also in the introductory meeting 2 weeks ago. So if there are more questions on the organization, you can find it there. I want to talk about Bayesian linear regression. Because it's a somewhat fancy concept, no? Particularly if you come from a frequentist world, like as all of us do, I assume. Yeah. So let's talk a bit more about this. So how does it? What are the exact differences from linear regression? what can be an advantage associated with it, what can be a disadvantage associated with it. Let's just talk a bit about it. I mean, I'm also mentioning it in the video, but mostly I want to talk about this associated graphical model. So the Bayesian linear regression is just a vehicle of having a slightly more complex model with a couple more variables associated. So let's collect a couple of some pieces of information. What do you recall, or what somehow what made sense or did not make sense from this concept? We can also start with standard linear regression. How does standard linear regression work? Mm-hmm. Mm-hmm.
And here, covariance matrix is the same. And
Mm-hmm.
if we compute, this point is belonging to some class 1.
Mm-hmm. So we have a supervised model, yeah. We have, you mentioned there's an assumption that the covariance is everywhere the same. We can maybe clarify this in a second. And then a prediction is made, not a class, it's a continuous value, no? But a continuous value, so prediction of a continuous value, yeah? Any memories about how this prediction is made mathematically? Yes.
And then we add bytes.
Mm-hmm. Mm-hmm. You can, or you probably would, or you would modify the input such that it's implicitly included. Yes. Yeah. Right. So you say there's an input of interest. Let's call it X, and there are weights, and you calculate an inner product. I forgot whether X is on the left or X is on the right, but it doesn't make a terribly big difference. So a scalar product between the input and the weights. And then you were correctly mentioning there's also an offset term, no? Something like a weight 0. And you can absorb this into the weights by just saying, yeah, okay, if for the input, if I have my normal input and a pseudo input here, which just corresponds to a 1, then in my weight vector, I can make this W0 part of this weight vector, then I don't need to write it explicitly. Yeah? Okay. So this is the normal linear regression. How do you come up with these weights? Because that's like the only ingredient, no? So our prediction Y is input times weights, and this pseudo one here added. Yeah. Okay. So how can you come up with these weights? The weights are fixed, yeah, but during the training they are determined. No? During testing they are fixed, and in the training, there's a calculation to find the weights. Yeah. How? Yeah.
I mean, there are many ways we can initialize them, but
Uh-huh.
the most simplest would be we just assume there is some distribution and we just randomly draw weights
Mhm.
from it
Mhm.
initially, and then the main goal of machine learning is basically to optimize it
Mhm.
through some
Mhm.
algorithm and loss functions such
Mhm.
that we have like least training error.
Okay. Yeah, in principle, yeah. So we need an objective function, right? And then using training data with associated labels, one would optimize towards that objective function. Now, there are different ways of optimizing things. No? For neural networks or so, it's usually an iterative procedure, iterative optimization algorithm. The beautiful thing is for linear regression, you don't even need an iterative algorithm. You can, if you assume a least square error, or you say you want it to be optimal with respect to a least squared error, then you can give a closed form solution. It's perfect, simple. So simple in a way, in the sense that you can do it with a couple of matrix multiplications. Yeah? So the way how it works is you have a number of these examples x. You write them in a matrix. So this is a whole vector x1, a whole vector x2. No? You collect them in a matrix x. You collect the associated target labels in a vector y. And then you can say, okay, so I can calculate these, how many training data do we have? We don't know, let's say n. No, n is here, sorry, let's say m. If we have m training data points, we can simultaneously evaluate them by multiplying them to this one weight vector. And if we now want to fit this, we can say, okay, it's perfect. We only need to solve this for the unknown weights w. So we have an equation of the type y equals x times w, where w is unknown. So all we need to do is bring x to the other side. Okay. Now we said, okay, not everyone did listen to or did attend pattern recognition, I know this. But if you attended pattern recognition, then you'll probably recall that this is not necessarily a square matrix. So you can calculate a pseudo-inverse by multiplying x transpose from the left. Yep. Now it's a squared matrix. So this, and if it's a positive definite, okay, so these are all details. You multiply this again from the left with x transpose x inverse. Then it vanishes on the right-hand side. And on the left-hand side, you have this expression. And this is your closed form solution. So it's like a matrix multiplication, an inverse, and a transpose, and there you go. No? Okay. And then you get predictions. So this is the linear regression. Now, what did we say changes with the Bayesian linear regression? Yeah. The weights are distributions, yeah. And this is actually not a small change. It changes quite a bit. No? So in this little calculation trickery here, these weights are specific coefficients, yeah, that like floating point values. Now, in Bayesian linear regression, the weights are distributions. And when I learned the first time about this, I found it very mind-blowing. Like, what? Like every weight, the distribution is just like crazy. Huh? But it's actually a quite powerful idea, and it addresses a problem that we like to ignore oftentimes, no? Namely, that this training data that we're seeing here, the X and the Y, this is actually, I mean, who says that this X and Y is a good choice? No? And this becomes a practical problem, or can become a practical problem if you're trying to advise someone, no? And someone says, okay, I use this and this and this for training data, is this a good choice? And then you have to say, yeah, I don't know, no? It's I mean, it's one choice, certainly, no? But there could be other choices. And this is unfortunately always true. So you could say there's like a sea of possible training data sets. That all make sense for the problem. I mean, we're not discussing the case that someone asks something unreasonable, but just for the very problem description, there's a, let's say, infinite amount of data, at least theoretically, and you make you're sampling essentially a certain choice of training data points, and you say, okay, this is my training data set. No? And you can say if you fully repeat the whole experiment, then you would send someone else out to collect training data. And this someone else would maybe collect this point, and this point, and this point, which is also, it's totally valid training data. It's drawn from the same distribution. Yeah? But then, if this person trains a linear regressor, and that person trains a linear regressor, they will be a bit different. So you could say, okay, like now I'm solving this the hard way. So I pay 100 people. They all should collect 100 data sets. They all should train this linear regressor. And then I look at the weights that they calculated, and I take the distribution right from their weights. No? Would be a possibility. And then we can use our kernel density estimator or so and have the distribution of weights. But of course, this is very expensive and cumbersome. No? And you can improve things a bit by assuming a parametric model for various distributions, and then carry the calculation through with parametric models of these densities. Yeah? Okay, so there's a lot of input. So let's go one step after another, and we don't need to go through all the equations. Whoever wants to look at the very equations, yeah, they are in so the calculation is in Bishop's book, chapter 3. I forgot the subchapter, but there's something like Bayesian linear regression. Yeah, and he goes through a numeric example. But it would be a bit too much for us now. But we can talk a bit about it. Yeah? You can, for example, and we can look at our graphical model and draw some information from that. because we actually have more information than just, oh, the weights are a distribution and the data is a distribution. Yeah? So we do have information about these hyperpriors. No? Here, alpha, we said, this is a standard deviation of a Gaussian. So apparently, we have this assumption that the weights are all draws from a Gaussian distribution. This is already a big help. So this is our parametric assumption here for the weights. Yeah? And so it means that this Gaussian is something that needs to be carried through these calculations. And at the end of the day, what you're adjusting are the standard deviations of this Gaussian. And the other assumption that and we don't have a particular assumption here about the data. The actual observations here will be plugged in, and there's a noise term. So there's an assumption that observations might be correct up to a standard deviation of sigma squared for problems with our measurement process for some reason. Yeah? Okay, so these are the two ingredients that constrain the calculation of this model. Yeah? And it's interesting that this is sufficient. So, okay, so what would you get? So you could, for example, say, I now want to make a new prediction for an unknown sample. No? Pretty much like we did it here for this frequentist approach. We just take we say we have a new position that is of interest for us, this x hat, and we want to make a prediction of this label at this position. Yeah? So this means that we need to marginalize over all possible weights that could be assigned. No? Marginalizing over all possible weights means if we would like to do this exactly, we would have to evaluate an integral over all these weights, no? Which in most of the cases doesn't work. And we will see examples later in class to see how we can how we can approximate such an integral with a sampling-based solution to get a nice approximation. No? Nevertheless, with a Gaussian, maybe you have even a chance to analytically integrate this. No? But in general, it's not possible. But then what you get is a distribution of outputs that resembles the distribution of weights that we had covered in that model through these different Gaussian distributions for these, for these weights from which we sampled them. Yeah? Okay. So it accounts for this additional uncertainty in the observed data. Yeah, so if we say what can be a potential advantage of this, no? So by obtaining a distribution of possible outputs, so we say we are interested in a prediction for position x hat, yeah? If we obtain a distribution for the output, then now I can phrase this as a question. What could this distribution, what type of distribution could one get from What type of information could someone get from that distribution that would not be available in our frequentist linear regression case? I can give you a couple of distributions just for the sake of discussion. So let's look at some. So we could look like this, could look like this. I'm not sure whether this, actually I did not think about it, whether this is possible, but let's just, for the sake of argument, let's just take it. What could you possibly read into them? You could take a mean, yeah, like a weighted mean then, no? But okay, but this depends a bit like how heavy this tail is. No? It could even end up at a location that is a bit counterintuitive. You could take the maximum, could say, okay, like my prediction is the maximum. Where's here the maximum? I don't know, here maybe? Here it's a bit tricky. Okay, here's this implausible distribution, but nevertheless. No? You could say this is my maximum likelihood estimate, but then so is this. Yeah, this is also a maximum likelihood estimate. So we didn't, like we made a lot of effort to get essentially at where we were like already in the last semester. So what extra information could one get out of this? Yeah. You can calculate some moments on top of it, yes. To get what? To get some measure or so, some understanding about the uncertainty that is associated. Yeah, and this is actually great. No? So if the distribution is relatively narrow, yeah, then like one assumption that you could make, no, is that, okay, so apparently this uncertainty that we have about our input data, about our weights or so, it doesn't affect the possible outcome at this location x hat so much, yeah? Because in any case, the result is a relatively narrow distribution. Yeah? Here we have the opposite. It's a super wide distribution. No? So it means actually our, like the family of our models, yeah, like all, if we set different weights compatible with our possible data that we can draw, they come to all different solutions. No? So in other words, our model has no clue. No? So it's probably not a good prediction. So it could be this value, but it could also be any other value. Yeah? Okay, and here it's even, again, disclaimer, I did not look close enough at the math to know whether this is really permitted with the model calculated through in chapter 3 of Bishop. But if we would have a bimodal distribution, that would be a particular case of having no clue, in the sense that there would be some acknowledgement about structure in the data, no? Because apparently it's not just squished out, but there are multiple plausible interpretations, no? Which is probably also bad. So in any case, the shape of that distribution tells you something about the suitability of your model and the reliability of your prediction. Yeah? What could be, let's try to reverse engineer this a bit. What could be a possible situation that such an uninformative or such a very good prediction comes out? maybe can we somehow reverse engineer a case where we have either one or the other? Just make some hypothesis, just draw something up. What could happen? Should we go one step back? Does it move too hastily or so? Then just tell me. We can backtrack or fill some gap somewhere. Are we fine up until this point? Does it make? Whoops, sorry. Does it make sense? No? Yes? Okay, let me go one step further, and then we can try to figure out, and then we can discuss what got lost underways. Yeah? Okay. What if we have a data manifold that somehow gives us information here about our function? I don't know, with a little bit of noise. Let's say it's a curve like this. But we ask about a point here. That would be a case where many different predictions are possible just because of the fact that if we select a couple of locations here, we get some noisy data estimates here, and we fit a curve. And if we really imagine sending out these 100 servants, getting us 100 other data sets, they would be slightly different. Yeah? So it would be like this. Maybe we would get a fit like this. Maybe we get a fit like this. No? So if we look at this location, the variety of possible solutions that we got is really wide. But it just comes from the fact that we are fitting something that looks a little bit like a squared function, no? To some data over here, and if it wiggles a bit, it can then change a lot if we evaluate this polynomial far on the outside. So a lot of different results possible, which is a bit resembled by this wide curve of possible outcomes. Yeah? The opposite situation could be if we are probing for a location here. No? So if this is, for example, like no matter how we sample, no, it's always well covered here with the observations that our servants brought to us, no? Then yes, there is some variability. Okay, there's even a big outlier here, but usually there's not a lot of variability there, yeah? Which then leads to a narrower prediction here, for example. No? And this is like, let's say, part of the overall mechanism, so we don't need to do some extra accounting for this, like, for example, try to understand where are the boundaries of that space, because in higher dimensions this gets super ugly again. It's just built into the mechanism. Yeah? So this, for example, is a very nice benefit. No? What can be a disadvantage of this whole? Okay, sorry, I promised to backtrack upon demand. Shall we backtrack, or what what aspect do you want me to follow up on? Okay, we can let this simmer for a while and we can come back to it, maybe also next week or so if you want, yeah? Mm-hmm. Sorry?
You try to defend the advantage of Bayesian linear regression by this.
So these three distributions here on the left. So let's say indeed that we want to fit a squared function, yeah, just for the sake of example, yeah. If we would analytically write this down as squared function, it would be something like 8 or W1, no, sorry, W2 x raised to the power of 2 plus W1 times x raised to the power of 1 plus, here's our bias term, W0 times 1. Now we have a squared function. Now, now we replace these scalar values by distributions. We say, okay, we make an assumption this is Gaussian, centered around 0, and so on and so on. So each of these is a Gaussian. And now what we can still fight, okay, like what exactly do we control about them? Do we really have the mean fixed? Is the mean adjustable and so on? What about the standard deviation? But three different Gaussians come out of this. So now these Gaussians are fixed during training. So it means I have a mean value mu2 and I have a standard deviation sigma 2, mu1, sigma 1, mu0, sigma 0. And now someone comes and says, I want to have a prediction for x hat. And then we say, yeah, okay, so if we would analytically solve for this, yeah, maybe we can't do this, but if we would want to analytically solve for this, then we would say, okay, these three distributions here, they actually describe a whole family of functions, yeah? Because my first weight could have this value, or this value, or this value, or this value, and the relative, so the associated probability mass in that distribution for a little area here, that tells us how likely is it that we are seeing this weight at the end of the day. Yeah? So, and this holds for all three distributions. So if we don't have a clue how to analytically integrate this, we could also say, let's draw some numbers. So I'm randomly drawing from this Gaussian, from this Gaussian, from this Gaussian, and then I have a first polynomial that makes this prediction. This is one of these curves here. Yeah? And then I can repeat this because drawing numbers is relatively cheap. So I can draw three numbers again, get a polynomial, and it gives me a second curve here. And I can repeat this, let's say 30 times. 30 is a good number. It's not an arbitrary choice. So it means I have 30 polynomials that I can, in principle, plot. And then at a certain location, I can check what is the variance here of these 30 different polynomials that I drew. And this is the variance of my estimate here. Yeah? Does that make sense? So the math is a bit involved to really carry this through. I mean, it's not super secret math, so it's chapter 3 after all in Bishop, no? But it's a bit messy. But the outcome is actually very simple. You can say, okay, then I draw 30 functions from these distributions, and I check at my position of interest how much is their spread. Yeah. Yeah. No, you can. I mean, yeah, for practical reasons, probably yes. But theoretically, there's no need to limit it to a Gaussian distribution. No? Yeah. Okay. Yeah, a disadvantage of this can be that if you say, okay, I mean, what you're addressing is actually a disadvantage, no? Like, how would you know that a Gaussian is a good model for this? And then let's start to talk about hyperparameters, no? Like a prior for these Gaussians. How would you know what is a good prior for this Gaussian? And you can say, okay, then I take, I can fix this. I take an uninformative prior, like something that is very wide, very arbitrary, no? But then you're giving up on one of the super benefits of a Gaussian model that you could define a prior. No? But it's not just a possibility, it's also a bit of an obligation to come up with a prior that makes sense. Yeah? And this is, I think this is one of the difficulties with these Bayesian approaches, no? That oftentimes you have no clue about the prior or hyperprior, depending on how many orders of this model you stack on top. No? Yeah. Okay. This was lengthy. Let's do something quicker. Yeah. Observed versus unobserved variables. What was this? What was the difference between these observed and unobserved variables that we discussed in the Bayesian network? Yeah. Okay.
So what I understand is, suppose let's assume that we are plotting it for a quadratic best.
So during the training phase. Okay, so if you introduce a random variable in such a construction, if you introduce a random variable, you need to attach either observations to it. This is what we see for the Tn. It has this observation xn associated, or you need to attach a prior to it to say, okay, like from what should I get this distribution? No? So this is the prior. No? And here in this case, I think we were just saying, yeah, we fixed the standard deviation of a Gaussian from which these weights are drawn. But how did we come up with this? Well, we just invented it. No? It's not justified by a reason, like a physical model or something. Yeah, the physicists actually, they are in a very favorable position here because they in many problems, they have a possibility to define a meaningful prior because it's physics after all. No? But in many more, let's say, general data science type of problems, you wouldn't know like what prior is appropriate. No? Okay, Shall we move on? So we talked about this conditional independence. It's already here, more or less in view. We had this notion of observed variables there and unobserved variables. How? Let's just try to come up with some language here. So if I have a graph like this, a dependency structure like this, this is A, this is C, we say it in the slides, this is B, 3 random variables. What role plays this property of, oh, I observed a variable here? It's about the calculation of the neighborhood. No? We looked at this middle variable, no? And said, if this is given, then somehow the communication here changes. Yeah? So what is the idea? So if we say, we have an observation here, C has a specific value, for example. And then we said this arrow, this is a conditional probability. No? So we have here the probability of B given C equals 5. So given 5 is a specific value. So this means that in a table having, let's say, all possibilities for all combinations of B and C and maybe even A tabled up, we know exactly we have to look into that column where C is 5 because it's a fixed value. And along that column we can read out the distribution for B. Yeah? So with that, there's no possibility that different choices of A, for example, could influence anything, our knowledge about the distribution of B, because our knowledge about the distribution of B is already totally specified, let's say, or at least totally constrained by knowing that C has the value 5. No? If we wouldn't know that C has the value 5, so if this is arbitrary, no, then things would change. No? If we would now, for example, read somewhere, oh, A has the value 2, then this would constrain the choice of C to that row in the table where A has the value 2. So this would change this distribution in a specific way. And this change would then in turn impact the distribution of B. Yeah? So with making an observation at C, we can break this chain. If we don't have an observation of C here, then indeed we can have this form of, let's say, remote influence of one variable to the other. So it works in this direction because we have these conditional distributions, but what you have to keep in mind is it also works in the other direction. This is a bit surprising maybe, but if you know that B has the value 3, let's say, no? Then you can start to think backwards. So it's like, oh, I know B has the value 3. So let's calculate for the possible reasons that might account for the fact that B has the value 3. So this is what we call inference. This is inference, turning around the arrows in this reasoning. No? So this means what could be the underlying reason for seeing a 3 here. Yeah? So in a classification setting, we would say C is the underlying class, no? For example. No? So this means you can say, okay, so knowing that this is a 3 changes my belief about C, and in the very same mechanism, it changes my belief about A. Yeah? So, but now if you for some reason already know, C, I know C is 5, then again, this breaks this chain. I mean, of course, if we learn now that B is 3, we can say, yeah, okay, apparently it somehow ended up being 3 in presence of the fact that C is 5. But learning about this does not change anything about A anymore, because A is already, let's say, constrained by the fact that C has the value 5 here. Yeah? So again, also in the backwards direction, knowledge about C fully determines our knowledge about A. No? So it wouldn't be changed by the B anymore. I think there's some benefit in going through an actual numerical example just to drive this home. Yeah? So let's go through this burglar example. It's the most complicated example, but we can then also, I think, relatively easily bootstrap the other examples from that. So here's a scan of these 3 book pages. I wrote the literature source here. The last name of the author is written Mack with an A. I screwed this up, sorry, M-A-C-K. But it's a very beautiful book, I have to say. Old book, but good. Okay, let's read through it really quickly. Interestingly, the chapter is already an interesting bit of information. It says exact inference by complete enumeration. So we have a categorical distribution, and we can go through all examples here and calculate this through. We open our toolbox of methods for handling probabilities by discussing a brute force inference method. Complete enumeration of all hypotheses and evaluation of their probabilities. This approach is an exact method, and the difficulty of carrying it out will motivate the smarter, exact, and approximate methods introduced in the following chapters. Okay, so please feel motivated. Let's have a look. The burglar alarm. Is it large enough? You can read this, right? Yeah. So here's the graphical model, but let's read through the text really quickly. Bayesian probability theory is sometimes called common sense amplified. When thinking about the following questions, please ask your common sense what it thinks the answers are. We will then see how Bayesian methods confirm our everyday intuition. So example 21.1. Fred lives in Los Angeles and commutes 60 miles to work. Whilst at work, he receives a phone call from his neighbor saying that Fred's burglar alarm is ringing. What is the probability that there was a burglar in his house today? While driving home to investigate these 60 miles, Fred hears on the radio that there was a small earthquake that day near his home. Oh, he says, feeling relieved. It was probably the earthquake that set off the alarm. What is the probability that there was a burglar in his house? So this is an example by Judea Pearl, but I didn't look up the original source. But Judea Pearl was this guy carrying out this proof that I'm briefly mentioning, that smoking is harmful. Because like the tobacco corporations, they were always saying like, there's a correlation, you know. How can you say it's harmful if all you do is look at correlations? Okay, so it's one of these superstars in this, let's say, probabilistic reasoning business. Shall we copy this model here really quickly? So our model is this. Maybe we should go backwards. So if there's an alarm, there's a phone call by the neighbor that the alarm is on. There's a and the alarm can have different reasons. So it can be a burglar, can be an earthquake, but if it's an earthquake, then one would probably hear also in the radio about it. No? Okay. So let's introduce variables B. A burglar was present. A, the alarm is ringing. P means Fred receives a phone call. E, a small earthquake took place. And R, there's something on the radio. So this means we're dealing with a joint distribution of 5 variables, P of B, E, A, R, and P and R. And this factorizes according to this dependency structure that we thought about. So we have the prior of having a burglar in the house. Then we have the prior for having an earthquake. Then we have the probability that the alarm goes off. This is determined by whether we are having a burglar here or we are having an earthquake here. Then we have the probability that we are getting a phone call. And we have the probability that there is something on the radio if there was an earthquake. So now I'm not going to write every single equation on this because it goes on for 3 pages, but we have this for reference now. And we need to assign to each of these events, or we need to either assign or calculate for each of these events a probability. Yeah? So let's have a look here. So the probability that a burglar was there, in fact, shall be beta. And then there can also be a counter event. There was no burglar. That would be 1 minus beta. For earthquake, the same thing. Probability for earthquake shall be epsilon. No earthquake shall be 1 minus epsilon. And this epsilon, let's say, is just 1 divided by 1,000. Our assertion that the earthquakes are independent of burglars, that is, the prior probability of B and E factorizes into a product probability of B times probability of E. Seems reasonable unless we take into account opportunistic burglars who strike immediately after earthquakes. And this is actually a thing, and this is a limitation of our model. No? But okay, let's exclude this for the time being, and let's just make it explicit that we are assuming that they are independent. So then let's talk about the probability that the alarm rings. So we assume the alarm will ring if any of the following three events happens. First, a burglar enters the house. This is the whole purpose of the alarm. And we have a 99%, let's say, reliability that if there's a burglar, it triggers the alarm. Second possibility, an earthquake takes place and triggers the alarm. So here's an assumption that 1% of alarms, alpha E, 1% of alarms are triggered by earthquakes. Or possibility C, some other event causes a false alarm. Let's assume the false alarm rate is 1 divided by 1,000, so Fred has false alarms from non-earthquakes once every 3 years. Okay, this type of dependence of A on B and E is known as noisy OR. Okay, with this we can now start in the calculations, and now it becomes clearer why this is called like a brute force enumeration method. So what can possibly happen? There are different possibilities for not having an alarm. So what are the possibilities for not having an alarm? It could be there's no burglar, there's no earthquake. Then it would just be the counter event to a false alarm. So having no alarm with no burglar and no earthquake means it's just a normal day. Or any combination thereof, we have a burglar or we have an earthquake, or we even have a burglar and an earthquake, and we can plug in the corresponding terms and calculate through that. And the very same thing for the possibilities of having an alarm. In that case, if we have an alarm, but there's no burglar, no earthquake, it's a false alarm. And again, we have the three possibilities: a burglar alone, an earthquake alone, or a burglar and an earthquake as a pair with the associated values plugged in. McKay is kind enough to do the math for us. It gives us these different probabilities. Yeah? And if we just look at the values really quickly, so some of these probabilities are really high, 99.9, 98.9, and a little bit. Some of these probabilities are really low. So it's very bipolar, we can say. Let's continue. So these are the values for this middle node. Now, we assume the neighbor would never phone if the alarm is not ringing. So the neighbor is perfectly reliable. And that the radio is a trustworthy reporter too. So also the radio is perfectly reliable, so no false alarms there. We won't need to specify the probabilities in order to answer the questions above, since the outcome phone call or radio gives us perfect certainty about the fact whether an earthquake happened or the alarm went off. We can answer the two questions about the burglar by computing the posterior probabilities of all hypotheses given the available information. Now it's interesting. Now we're turning things around. Yeah? So we say the values that we calculated so far were if we know about an earthquake or if we know about a burglar, we have some probability that this alarm will go off. Now we say, now let's try to think in the other direction. So if an alarm went off, what is the probability that it was actually the burglar? Okay. So let's start by reminding ourselves that the probability that there is a burglar before either the phone call or the radio are observed is just 1 in 1,000. And the probability that an earthquake took place is also 1 in 1,000. And these two propositions are independent. Okay, we talked about this. Okay, if we get a phone call, we know that the alarm is ringing. So let's have a look at the posterior probability for the burglar and the earthquake if the alarm goes off. So we plug in our Bayesian equation. We have the likelihood here. This is what we calculated already. Then we have the prior probability for burglar, prior probability for earthquake, and the total probability that an alarm goes off. The numerators for possible values are alarm goes off in all cases, but now all combinations of burglars or earthquakes times the associated prior probabilities. And now what we see is that we have, if we look at the resulting values, what we see is that we have a super small value here for alarm went off and a burglar and an earthquake occurs. We have a small probability here, like 1 in 1,000 approximately, that alarm went off and a burglar occurred here. And similarly, that alarm went off and it's just a false alarm. So nothing happened. And it's even less likely that alarm went off and it's an earthquake. The normalizing constant is the sum of these four numbers, and the posterior probabilities are, and here we can see it better. So it's a 50-50 chance, more or less, that there's a burglar or it's just a false alarm. No? So the earthquake is also a possibility, but it's relatively low, and earthquake and burglar is super low. So to answer the question, what is the probability a burglar was there? You need to marginalize over the earthquake variable E. So the alarm goes off, and we go over all possible earthquake events. So it was either an earthquake or it was not an earthquake. So the only variable that is left is burglar was not here or burglar was here. And we sum over no earthquake or earthquake. And we get a 50.5 chance for no burglar was there and a 49.5 chance that a burglar was there. So there's nearly a 50% chance that there was a burglar present. It is important to note that the variables B and E, which were independent a priori, are now dependent. The posterior distribution is not a separable function of B and E. This fact is illustrated most simply by studying the effect of learning that there was indeed an earthquake. So what happens now if we have that earthquake? Then the posterior probability of having a burglar is given by the probability there was a burglar given there was also an earthquake and the alarm went off. So this is the probability there was an earthquake, the alarm went off given, there was of a burglar, the earthquake given the alarm went off divided by the total probability there was an earthquake and the alarm went off. So long story short, the calculation ends up being a 92% chance that there was no burglar. Yeah? So knowing that in fact it was an earthquake changes the whole belief about the fact whether there was a burglar or not. It's still an 8% chance, but this is no comparison to the 49.5% chance that we had before. And this is, so McKay writes, it is in accordance with everyday intuition that the probability that there was a burglar reduces when Fred learns that an earthquake, an alternative explanation of the alarm, has happened. And this is called also explaining away, no? That you say, okay, now I have one explanation, and this is actually already, for me, is already proof enough. Okay, this should explain my view of the world, my observations. No? So there's no need of making further assumptions about burglars or so being at my home. Okay, sorry, it was a long example, but I think it's very helpful to see for essentially binary variables, you can enumerate these values, no? All possibilities, and then gradually plug in the knowledge that you learn as you go, and see how the belief about the unobserved variables changes. Okay, let's get some air. Breathe, breathe. I think on Thursday, Sheetal has a slightly smaller example. The other examples are much simpler. No? If you have a chain of these three variables, it goes relatively easily through. No? The problem with this is, okay, we saw the problem that we have to get to a belief first, and then need to update this belief by learning about one of these variables, and this makes the calculation a bit lengthy. No? But I hope you agree it's elementary. It doesn't use any advanced mathematical tools or anything. It just needs thoroughness to keep track of things. No? Yeah. Okay, what else do we want to talk about today? Yeah. The lecture slides? Yeah. Mm-hmm. Sorry. Which slide? 15. Oh, physically 15. This slide? Okay. Maybe I misspoke there. Yeah, you mean in equation 9? Yeah. No, it's the chain rule, right? Yeah. Did I say product rule? It's probably yeah. No? Sorry. No, they are not the same. They are not the same, sorry. Let's get some Wikipedia knowledge. What did we say? Chain rule of probabilities. The product rule, yeah, sorry? Yeah, sorry. It was Saturday evening. It was a long week. Maybe I said wrong things. No. It's. I mean, it can very well be a mistake. I mean, it's not like I'm not like a saint or anything. So if I say something that doesn't make sense, like the most likely explanation is it's a mistake. No? Sorry. So marginalization means that you are, what is, no. You guys tell me, what is marginalization? Someone. It's late, but we gather our power and explain marginalization. What is marginalization?
I remember from like PR, so it's like when you want to find the values of y,
Mm-hmm.
by root, so you minimize the values of x
Mm-hmm.
in the denominator.
Mm-hmm.
So you look the values of y, something like that. It's like a mathematical expression.
Yeah. You definitely need it to evaluate such a Bayes equation. But let's very much to the point. What is marginalization? Sorry? It's not just an assumption. It's actually like a calculation technique. Or maybe I didn't hear you properly. Sorry. Okay. We have it right here. Sorry, we had it in our example of the earthquake. So here's a marginalization over the earthquake. Marginalization means we want to have a probability that does not contain a certain variable. Like in this particular case, in this equation 21.6, we want to get rid of the earthquake on the left-hand side. Yeah? So this means in this expression, like we have our expressions with the earthquake, and the earthquake can either have happened or it has not happened. So these are the two possibilities. So if I want to get rid of the influence of the earthquake, then I have to say I have to take account for both possibilities. So what happened in case that there was an earthquake? What happened in case that there was no earthquake? So this is a summation in the discrete case, or in the continuous case, an integration over all possible values of that variable that I want to get rid of. Let's appreciate this equation a bit more. We are interested in the probability that there was no burglar, given that the alarm was raised. What we have is the probability that there was no burglar and there was no earthquake, given the alarm was raised, and we have the probability that there was no burglar, but there was an earthquake, given that the alarm was raised. So the marginalization is the process of integrating out this variable, v, whatever it is, from my expression here. So I have something a, b, v. The marginalization is to integrate over all possible values, v, and then I obtain a, b, so. No? So the v is gone, because I enumerated all possible outcomes with their associated probabilities. Yeah? So everything, all outcomes for earthquakes were accounted for. These are very elementary things, and if you want to know more about this, you can have a look here. So I'm briefly mentioning them here. I understand that this is super brief. This is a joint distribution. We have a conditional. Here we have the marginalization. Here's the product rule. But I haven't listed the chain rule. Anyways, I gave a literature reference. If you feel like, okay, I should refresh this somehow, then have a look at the book by Bishop, section 1, 2, 3. Now, this is the actual section. It's chapter 1, part 2, sub-chapter 3. Yeah? Okay, so have a look there. So it's a quick recap or get a copy of this book. It's also good. No? Or yeah. Okay. Shall we call it a day? Then thank you and see you then.